Good morning, all of you. In the last class, in the Bayesian classifier for normally distributed classes, we have seen a couple of examples where we noted how the decision boundary would be there for varying values of covariance matrix, as we could see here in this example. Now, the first example was the case where you have an elliptic boundary there. The second example is there where you have a hyperbola as a kind of your decision boundary. And we have also in theory have seen, suppose if the on diagonal elements are same with zero off diagonal elements, this would be a circle that we have seen. Now, after that, we have considered a special case where the covariance matrices are same for all the classes. So that covariance matrix sigma I equal to sigma for all those classes. Then we further redefine our see the eventual goal is to look at how the decision hyperplanes would look like, what would be the equation of that. To achieve that, as a first step, we have looked at how the function, discriminant function, which is a monotonically increasing function, would look like. Then again, in this process, we have also dropped some of the terms. For example, this covariance matrix is same for all. So when you are computing the decision boundaries, this is not going to have an impact. So we dropped this term. Then we simplified that further and we figured out that this discriminant function is a linear function of the feature vector x bar, right? This is what we have done in the previous class. Now, in this class, we'll continue our, our travel for arriving at the decision hyperplanes. Now, you have the discriminant function gi of x bar, which is found to be linear. Now, we will see, we have also seen an example showing what it means that being a that being linear. For example, means varying mean vectors, but the same variance value, this would be how the plane would look like. Okay, this is where we stopped. Now we further continue our discussion into actually computing the decision hyperplanes, right? So what we are going to compute, the goal is same as what we did in the last class. We want to compute the decision, we want to compute the decision hyperplanes. That's what we want to compute. GI of x bar, if you recollect, this is what I just copied it from the last class notes. You could see here, okay, GI of x bar equal to 1 over sigma square, the same term that you see here. I copied it here. So let me also further just, this is an optional one, but you gain some advantages with that. I just multiply it with sigma square again. You could think of it as again slightly redefining my function as it is more convenient. So this is how I do it. Gi of x bar is equal to mu I transpose into x bar, mu I transpose into x bar minus 1 by 2 into mu I transpose into mu I transpose bar into mu I bar. Of course, here also there is a bar because that's a vector, plus sigma square into natural logarithm of probability of omega I. Anywhere, if any of the steps are not clear, do let me know. Okay, I'll go with a little bit accelerated pace, but nevertheless, now it is your responsibility to stop me if any of the steps are not clear. Okay, so I would now write Similarly, this is a discriminant function for the ith class. As decision hyperplane means I would be eventually computing Gij of x bar, which is nothing but Gi of x bar minus Gj of x bar. So I'm also writing an expression for Gj of x bar here, which is mu j bar into x bar minus 1 by 2 into mu j bar transpose into mu j bar plus sigma square into natural logarithm of probability of omega j. Now I would write the expression for Gij of x bar, which is equal to Gi of x bar minus Gj of x bar. Now I would write away any mistakes I have written there. Yes, I did. Here I forgot to keep transpose there because it's just I replaced with j when it comes there. Okay, so this for the decision plane, if I want to compute, Gij of x bar will be equal to 0. That will give me the decision plane. So this equal to 0 will give me the decision plane. This is how Gij of x bar has been defined. So now you could see I can write it as mu I bar whole transpose minus mu j bar whole transpose into x bar minus 1 by 2 into mu I bar transpose into mu I bar minus mu j bar transpose into mu j bar plus, okay, plus sigma square into, or yeah, sigma square into natural logarithm of, what can I write inside this? Tell me quickly, otherwise I have to say on my own, otherwise it's taking too much time. What will I get inside logarithm? Single term. Probability of omega I.
I by omega j.
Very good. Probability of omega j is equal to 0. Right. So now I would further simplify this as mu I bar minus mu j bar whole transpose. I would write it. Either I could take individually transposes and subtract, or first you subtract the actual vectors and take transpose, right? Both of them would mean same, into x bar minus 1 by 2 into, do you see that mu I bar transpose into mu I is like x square minus a square minus b square term is what you have there. So I could write it as a plus b into a minus b way I could write it. Okay, so that way I could write it as okay, so I can write it something like mu I bar minus mu j. I would write whole transpose here because at the end it's a vector of 1 cross 1. So first transpose comes so that it will become 1 cross L multiplied with L cross 1 and resulting in 1 cross 1 into mu I bar plus mu j bar. Okay, in case if you are not yet very clear on how I have written, you simply look at multiplication of them. So mu I bar minus mu j bar whole transpose is nothing but mu I bar whole transpose minus mu j bar transpose. Then you see the multiplication. A minus b into a plus b you multiply, and you will realize that of course mu I transpose mu j is same as mu j transpose mu I. Those are the terms that cancel out, and finally only those two terms which were there in the above equation would remain. You hope you have already realized why I have written it in this particular form, because then I could take out common this mu I bar minus mu j bar whole transpose. Hope it is clear. Otherwise, just work it out. And after that, if it is still not clear, feel free to get back to me. Into sigma square into natural logarithm of probability of omega I over probability of omega j equal to 0. Now what will I do? That implies your Gij of x bar is equal to, I will take this mu I bar minus mu j bar whole transpose outside, common for all the terms. Then what do I have inside? X bar minus 1 by 2 into
Mu
mu
I
I
bar
bar.
plus mu j bar.
Very good. Mu j bar. Okay. Then I would get here plus sigma square into natural logarithm of probability of omega I over probability of omega j. Pay your attention here. This is little bit tricky. So I would write here mu I bar minus mu j bar divided by mu I bar minus mu j bar whole transpose into mu I bar minus mu j bar. This has to be clear to you. Pay attention here. Now look at, if I multiply it, see the numerator and denominator, if you look at, it has mu I bar minus mu j whole transpose into mu I bar minus mu j, correct? So which is a scalar. So you are just multiplying it with a scalar and dividing it with a scalar. Do you agree with that equation? Are any questions there? Is everybody able to follow that?
Yes, sir.
Good. Now, one more step I'll go. So this, if you want, I'll the same equation I would slightly modify writing it. So for example, I would take this whole, oh no, not there. I will take x bar minus 1 by 2 into, I will write. So since I have taken minus out, this that plus I am making it as minus, and since there is no enough space to keep that bracket there, for the time being I am removing it, keeping this bracket and then this double bracket. Okay, so that's what I just put minus out. And now what I would do is this, you look at this whole term, does it has anything to do with x bar as such? What is it dependent on? Is it dependent? It is dependent on the prior probabilities of I and j classes, the mean vectors of these two classes, as well as the covariance values of those two classes. So this is constant for given ij classes. So I would call this by name x naught bar now. So this is what I have. Then I would write that implies Gij of x bar is equal to mu I bar minus mu j bar whole transpose into x bar minus x naught bar. Very, very important result for us. Gij of x bar. What is it that we derived now? We have derived the equation for the decision hyperplane when you have the covariance of matrices of two classes being equal. And of course, we also assumed that the covariance, the elements of this covariance, the feature vectors are statistically independent. In other words, the off diagonal elements are 0. Then this is the decision plane that you would get between classes I and j. So now if it is 0, that gives you points across the plane, at the plane. And if your Gij of x, if you make it to 0, you will get decision plane. If whatever you got the value for a given x bar is greater than 0, that belongs to ith class, and less than 0 would belong to zth class. Okay, so you could say now GI is a for decision hyperplane. If you want to compute the decision hyperplane, what would then happen? Your Gij of x bar, you will make it to 0. What would be the result of that here? If I make it to 0, what would happen? What is the result of it? When will that be 0, in other words?
X is equal to x naught.
Very good. That's all. Your x bar is equal to x naught bar for all values of x bar, for which this x bar equal to x naught bar, this will be equal to 0. Okay, that's your x naught bar. I'm not, you could write the expression there, but just since there are too many terms, I'm not writing it. But I would take a special case again so that my writing will become simpler. Otherwise, you make a note there. This is your x naught bar. Let me again consider a special case of if your prayer probabilities are equal for both the classes. Assume that your I and J are equal to 1 and 2. Okay, if you want to be more specific, you could, otherwise we have not yet considered just two classes. So it's all right. You could write even probability of omega I is equal to probability of omega J you take. Then you tell me now what would be the value of x naught bar. You can look at this equation and tell me what is the value of x naught bar.
Minus half mu I plus mu j.
Very good. Very good. That's all. X naught bar is equal to, anyway, I have written it as x bar minus x naught bar, so that minus won't come. Okay. Is it not? Because whatever is there inside the brackets, I'm considering it as x naught bar. See, when probability of omega equal to probability of omega j, this logarithmic term is becoming 0. So this term would completely disappear, and all you are left with is 1 over 2 into mu I bar plus mu j bar. So you just take the line along this mu I bar plus mu j bar and take somewhere exactly in between. That is where you will have a hyperplane. Okay. Hope you could now correlate this with earlier examples that you did with the Gaussian distribution. If you recollect, we solved a couple of examples where we assumed the same variance, and we should accept that the mean, one of the mean is there at, if I remember correctly in that example, at 0, and another is at 1, one-dimensional case, and they intersect at 1 by 2, or maybe if it is 0, 2, it would intersect at 1, because you could see here the decision plane would be in between. So if this is the condition, x naught bar will be equal to 1 over 2 times mu I bar plus mu j bar. Okay. A similar thing you could also do. So let me, maybe before doing anything else, let me draw this for a example of 2D case so that we could draw things. Otherwise, for higher dimensional feature vectors, we won't be able to draw that. So let's take an example and draw this for L equal to 2, two-dimensional case we will take. I have here, let's say, my feature vector here is x1, x2, right? See, x naught bar is again a function of x1 and x2. That's all. Now, if my L equal to 2, so my x bar is a, everything is a function of x1 and x2, is it not? Now, let us consider L equal to 2 and also a two class problem we will consider. So this M is equal to also 2. That's what we are considering it here. Now, let's say for the first class, I have my vector of mu, what should I call? mu1 bar I will call. The mean value will have some particular values of x1 and x2. Assume that this is my x1, I know where it is. This is my x2. Then this will be my mu1 bar. I am trying to give a geometrical interpretation to this equation. So I think this line has been run with a tilt there or a slope there. Okay. Assume that I have a straight line there. Okay. Bear with my drawing. Okay. Now, similarly, I have second class is there, for which let's say this is my mu2 bar. This is my mu2 bar. That means this value will give me my mu2x along this x1. And of course, this would give me mu22 or mu2y, whichever you call it. So this is my mu2 bar. These are the points where the mean values are there. Now, before I further proceed, can you give me the relationship between mu I bar minus mu j bar vector and x bar minus x naught vector? Pay attention carefully. This is a very important stuff. These are two vectors, right? Mu I bar minus mu j bar is a vector of size L cross 1. X bar minus x naught bar is a vector of size L cross 1. Now, what can you say about these two vectors on the decision plane? X naught bar is essentially very good. They are orthogonal. Then only they will become zero. It is like a dot product of two vector. It is not like a dot product. It is indeed a dot product. Okay, there is no second thought about that. So I could x naught bar. I'm saying it for when this is becoming zero. So I could also say here, this is a very, very important result. To arrive at it, we have to do this all the math part. Otherwise, the interpretation could have been a little bit difficult. So what I could say is mu I bar minus mu j bar is perpendicular, right? This perpendicular to x bar minus x naught bar, where is that will give you perpendicular. So the decision plane is perpendicular to mu I bar minus mu j bar. That's what I could say. What does that mean? The decision plane, well, I could have called it hyperplane also for L greater than 2. But being L equal to 2, I could call it as decision plane is perpendicular. Very, very important. To decision plane is perpendicular to mu I bar minus mu j bar. Okay. Now, let's plot mu I bar. This is mu2 bar. Similarly, let me rewrite this also. This is mu1 bar. Okay. Now, mu1 here in this case, mu1 bar minus mu2 bar. Okay. Mu2 bar means now you take the mu2 bar means this would come in this direction. If you take, you all know vector calculus very well. Mu2 minus mu2 bar plus mu1, that is mu1 minus mu2. Then what should I do? I should connect these two. Okay, what will be the direction now? Minus mu2, mu1, they are coming together. So obviously, this would give me, this direction would give me what? Now, this would give me mu1 bar. This would give me mu1 bar minus mu2 bar. Right? So x bar, now if I want it, what would that be? That line is perpendicular to this. So somewhere, I don't know, you need to draw a line which is perpendicular here, right? rewrite with at least a little bit better version of that. Okay, somewhat better. This would be the line there. Let me extend it to further to intersect with x1 also. And now on mu1 and mu2, if you look at it, that will be, again, you could use simple vector calculus here, and you would realize that, or even from the equation, you would see this x naught bar is equal to mu1 plus mu2 by 2. So this, if you want me to plot, oops, what I did, me go back. Hope I did not close that. Where is my, okay, I'm still there. So let me draw this. Okay, this is my x naught bar. Okay, this x naught bar equal to half of mu1 plus mu2. Of course, this green line is the plane where it is perpendicular, and on the line mu1 minus mu1 bar minus mu2 bar, that intersection is nothing but your x naught bar equal to half of mu1 plus mu1 bar plus mu2 bar. And of course, things will be much simpler. You consider a case of even 1D. So that was mu1 plus mu2 by 2. This we have seen earlier itself while dealing with the Gaussian distributions. Two Gaussians which are having same variance but different mean values, the intersection is at the middle point. The intersection is nothing but the decision plane. Of course, that being 1D, you have a decision line there. Now you could, here this being two-dimensional feature vector, you could that, where is that vector? You are knowing it only based on that property of mu a bar minus mu j bar being perpendicular to x naught, x minus x naught bar, right? So this is what you got it. Okay. I will move to the next case where, suppose if the probability of omega 1 is greater than probability of omega 2, then what is going to happen? How do we know that? Come back here. Probability of omega I is, or I could write I or j, it's up to you, or 1, 2, you write it. Then you are subtracting it from half of mu I bar plus mu j bar, which means it will be moving to the left of it. Okay, so that means maybe I use a black color here. Is it still, will that be still perpendicular? Then your, notice here x naught bar is varying. That value is not anymore mu I bar plus mu j bar by 2. From that you need to further subtract sigma square into natural logarithm of probability of omega I by omega j into whatever is there. You are going to subtract that. But is that still x bar minus x naught bar, is that still perpendicular to mu I bar minus mu j bar? Is that still perpendicular or not? Hello? Is that still perpendicular when I have two classes with varying prior probabilities? Yes or no? Is the question clear? If not, you can ask for a clarification of the question. See, the first case we considered here is when probability of omega I equal to omega j. It was half of mu I bar plus mu j bar is your x naught bar. It's just that, notice that your x naught bar value will vary if this condition of probability of omega I, if the prior probabilities are not equal. So all that would happen is then your decision plane moves to the left. That's all will happen here. So, but still it will be perpendicular. Notice here, still whatever is the x naught bar value, that is still perpendicular. To find out the decision plane, you make gij bar of x bar equal to 0. So that x bar, okay, for which these are, then these two have to be perpendicular, correct? So that will move to the left. So hope in which, yeah. So let me draw that somewhere. So hopefully as much possible parallel to that, still perpendicular. So this is when you get it. Okay, just let me draw like this. This is what would happen to your decision plane when your probability of omega 1 is greater than probability of omega 2. And of course, the earlier one is for probability of omega 1 is equal to probability of omega 2. Okay, I could draw similarly for the other case also. This has, in this case, when your trade probability of omega 1 is more, it will move in this direction. The other case, it will move to the right. That's all.
So,
Yes.
sir, is there a necessity that the decision plane moves to the left, because it depends on the value of the mu also, right? The other
Yeah.
values.
I mean, yeah. You are absolutely right. I agree with that. And in fact, I take back my point also. Very good point. Can I say towards mu1 then? Then it is fine, correct? Is that fine then? This is mu I bar minus mu2 bar. So yeah, I agree with you. Suppose if mu1 instead of mu1 it is mu2, and if instead of mu2 it is mu1, that's your point, correct? So then very good, very good. I agree with that point. Let me see what has been written in text. Yeah, you are absolutely right. Thanks for pointing it out. That was a mistake from my end. So what I should write here is moves closer to mu1. Very good. If I write it this way, this is fine, right? Uh, so since you have here mu I bar minus mu j here, just look at here. So that you could say from the average, you would look at it. Okay. So that moves closer to mu1. That's a good point, right? Any other questions here?
In general, we can say it as mu, the one which has the greater mean value, right?
Correct. Right.
Same case.
Which has a greater prayer probability.
Mm. Yes, sir.
It
Like,
moves towards that which has a greater prayer.
yes.
Good. Very good. Excellent. In this mode itself, I'll show you some graphs here to, so this is what we discussed right now. Now, this decision plane, how critical it is to accurately find it out, and how is this related to the covariance matrices of the two classes that you would notice from this figure that you see here. Well, if the spread, if the each class is compact, what do we mean by compact? Is variance more or variance less? When do you call it class? When can you perhaps call a class as compact class? Should the variance be more or should the variance be less? When will it be compact?
When variance is less.
Correct. Very good. So when you see here in this image, when variance is less, of course, this is perpendicular, but um, uh, this line, even if you move it this side and that side, since the variance is same, you would again get the same decisions there. It is, so what you could say is when classes are very tight, right? Then these are, so what is going to happen now? You have noticed that it moves one side or the other depending on the prayer probabilities of two classes that we consider. So this becomes less when each class is compact. In other words, when the covariance of each class is small, the decision planes are less sensitive to the values of prayer probabilities. This is in practice, a very, very important observation or an important point. See, why is it so important is that you might not know the prior probabilities of the classes accurately. You would only approximate that. However, depending on these prior probabilities, this line is moving either to one side or the other. But it's all right. Even it has moved a little bit, still you will get the same results when you have compact classes. In other words, the variance of these classes is small. On the other hand, take this second example that you would see here. Any movement from the center of this would give you wrong classifications or large values here, correct? You should give it. So you could notice here this, when will that line would move, that would essentially the minimum one will be either minimum risk one or the one with minimum probability error. We have seen it earlier. But now what would happen is this line that will be no more the case if there is even a small, even there is a small error in your prior probabilities computation. When they are not compact classes, in other words, when the variance of these classes is high, there is a, then the decision planes are more sensitive to actual values of the prior probabilities of these classes, of the given two classes. That means the accuracies of these classes, prior probabilities, will play a very critical role when you need to make a classification between two classes that have an overlapping region, or those two classes with high variance, in other words. Okay, of course, if they are high variance, but mu is spread, this is again, we are talking for a given value of mu I and mu j. You could also consider a case they are having high variance, but their mu are very spread apart. Okay, instead of two classes having mu1 and mu2 like this, suppose I have some mu1 like this and mu2 like this, then it's a different even your variance. So this is more we are talking about for a given mean values. Okay, good. So if those two things are clear, I'll move on to some other derivation. Again, this is again, there's a very important role. So just would like to listen to you one more time before I move forward and do this kind of exercise for non-diagonal covariance matrix. So here I assumed that all classes have same covariance. I also assumed there that these feature vectors are statistically independent. In other words, the off-diagonal elements are zero. We'll make a derivation now to a case where we have non-diagonal covariance matrices. But before that, I just want to ensure that all of you are clear with all those things that have been discussed so far. Is that fine? Now what I'm going to do is for non-diagonal covariance matrix. This is what I would do now. Okay. If you recollect, the GI of X bar expression will here what I would do is, so what is this expression is mu I bar whole transpose into sigma inverse into X bar. Let me first write and then I'll explain you on that. Plus natural logarithm of probability of omega I. Okay. And minus 1/2 into mu I bar whole transpose into sigma inverse into mu I bar. Where from this expression has crept in? Let me go back to the earlier classes and show you where I was getting this expression for GI of X bar. Okay, look at here. This is from where I have GI of x bar, right? So there, yeah, this expression is good enough to begin with. Look at this expression, gi of x bar, this expression, you look at it. What would happen? 1 by sigma square we have written, the reason being that a diagonal element. If that is not a diagonal element, and to get a 2 cross, finally that's a, remember that it's a scalar that we get out of each term. So if you keep track of the earlier ones, I would have written this as mu I bar transpose into the sigma inverse would come, because then 2 cross 1 cross 2, 2 cross 2, 2 cross 1. So that would be coming there. So that will be mu I bar. So this term would come here, that will give me mu I bar transpose into sigma inverse into x bar. And of course, then I kept, that is what I have written as the first term. Okay, I think I unintentionally interchanged these. First, I have written natural logarithm of probability of omega 1. Then I have written again this term also, you apply the same logic there. 1 by sigma square is nothing but the value inverse that you get, okay, when it is a diagonal element. Now, this is a non-diagonal element. So this would become mu I transpose into sigma inverse into mu I bar. So maybe just I'll follow the same order also here, just to be consistent. So I would write here minus 1 by 2 into mu I bar transpose sigma inverse mu I bar plus natural logarithm of probability of omega I. Okay. Any question or any doubt here? If you track back from that equation to the earlier ones, where we assumed that it's a diagonal one, there 1 by, see if it is a, if so, if you still have a doubt, you just, if sigma is diagonal matrix, okay, this would help you to keep track of the earlier things and compare it with the earlier equations. Then what is going to happen if that is the case? Then your sigma inverse value will be equal to what? 1 by sigma square into, what should I write here? No, identity matrix. Look at this. Sigma is diagonal matrix. That means what would be the case? Okay, I'll just go back and write it even in simpler terms here. Sigma square. Okay, a minute. Sigma square 0, 0, sigma square, right? That implies my inverse matrix equal to 1 by AD minus BC is sigma 4 into D minus B minus C minus A sigma square 0, 0, sigma square. This is equivalent to, I could take sigma square out. That would give me 1 by sigma square into I. Hope at least now you are convinced. Are you convinced? You substitute that, you will get the earlier equation. Okay. Yeah. Now, what I will do now is I want to compute the, what is my goal now is to compute the hyperplane. How do I compute that? By making Gij of x bar, which is equal to Gi of x bar. So these are from the discriminant functions. I am getting the hyperplane or a decision plane here. I should rather write it as a decision plane rather than hyperplane. This is the decision plane I want to get, is equal to Gi of x bar minus Gj of x bar, that being equal to 0. So I would right away, now we have written enough of these things. So I want to, no need to go even intermediate multiple steps. So let me write that here. What would that result in? So Gi of x bar, I will write the corresponding terms in one place. So mu I bar transpose into sigma inverse into x bar. When I subtract from that Gj bar, I would get there. In place of I will get j. So mu j bar transpose into sigma inverse into x bar. Okay, in the textbook there are not the derivation, my intermediate steps are not given. Since you may find it later a little bit trickier to figure it out, I am writing these steps, so please follow that carefully. So 1 by 2 into, then what do I have there? Second term is mu I bar whole transpose into sigma I inverse into mu I bar, right? The other term when I write, of course, minus of minus, that will become plus 1 by 2 into mu j bar transpose into sigma inverse into mu j bar. Okay, plus anyway logarithm, I will write it logarithm of log a minus log b equal to log a by b. So I will write it as probability of omega I by probability of omega j. Okay, this being equal to 0. Then what else can I do it here? Well, I could write this as first two terms as mu a bar whole transpose minus mu j bar transpose into sigma inverse into x bar. The first two terms I combined them, right? So then minus 1 by 2 into here, again in very similar lines, I would write mu I bar transpose minus mu j bar transpose into sigma inverse into, what do I get here? Mu I bar plus mu j bar. Again, notice here I am using the same trick that has been used earlier. What is the trick? A square minus b square equal to a plus b into a minus b. That's what I am writing there, for the obvious reason that I would like to take the possible common terms outside into natural logarithm of probability of omega I by probability of omega j equal to 0. Okay, now let me take mu I bar transpose minus mu j bar transpose out. Of course, why not take sigma inverse also? That also I can take out. Then what do I get inside? I would get there x bar minus 1 by 2 into 1 by 2 into mu I bar plus mu j bar minus natural logarithm of this derivation. Intermediate steps were not given in the textbook, so please pay attention to it. Otherwise, minus natural logarithm of probability of omega I over probability of omega j into same trick as you used earlier, mu I bar. Yeah, there is a, I missed a transpose, correct? This has been a transpose here. That was a mistake from my end. Correct. See this mu I bar transpose minus mu j bar, you will write mu I bar minus mu j bar whole transpose. Okay, right. So then here you get mu I bar minus mu j bar whole divided by now mu I bar minus mu j bar whole transpose into sigma inverse into mu I bar minus mu j bar. Okay, need to extend this till here. Maybe I have to put a double bracket or square bracket first. This equal to 0. Yes, it's a little bit of a mathematically bit rigorous, but at the end of it, what you see should be pretty clear. Similar to now the what I did earlier. Earlier I had here mu I bar minus mu j bar transpose. Okay, this transpose I'm keeping it outside. Okay, then it is fine. Okay, mu I bar minus mu j bar whole transpose I got earlier. Now in addition to that, I got here the covariance matrix inverse is also there with that. That's the additional thing I got here. And inside mu I bar plus mu j bar by 2 is there, same expression is there. I'm just comparing it with the earlier expression I got here when I have a diagonal matrix. So all that changed here is there is one term here multiplied with sigma inverse. Similarly here, while what does this term would give you, if you notice, that is nothing but the L2 norm, x square plus y square is what you are getting. In the L2 norm place, you are getting something slightly different, where you are getting sigma inverse there. Inverse matrix also you are multiplying it. So that is an L2 norm is nothing but a Euclidean distance. And this particular one where you are multiplying, instead of multiplying mu I bar minus mu j bar transpose with mu I bar minus mu j bar, you are multiplying in between with the inverse of the covariant matrix. If that is referred to, earlier one is referred to as an Euclidean distance. Does anyone have an idea on what this is referred to as? Very good, very good. Where did you come across this? That's right. This is Mahalanobis distance. I'll talk more about this in the next class, and with that, we will then move with the day in this itself the parameter estimations for these likelihoods and other things. Okay, with the next class, I'll be wrapping this up. Okay, yeah, I'll stop here.